From what we just saw above in this last portion, I'll just scroll up to it quickly, we have a relationship that describes how the motion of material, downslope, is linearly proportional to that slope via a constant of proportionality, and that this constant might relate to things in climate, lithology, and land use. So, if we want to take that expression providing the simple relationship for the motion of Hillslope material and convert it into something related to the form of a landscape, which is what as geomorphologists we care about, we need to use a good old tool that we know and love called conservation of mass. So I'm just going to underline this right here because it's important, so underlined and italicized. And what we're going to do, if we're properly accounting for material density, we can also refer to this as conservation of volume, which is essentially a simplification of conservation of mass, assuming that there's no change in volume of anything. Some change in volume might occur, with soil formation, weathering, and so I'm just going to put a couple big exclamation points there. So if we're thinking about those sorts of processes, then we can't use conservation of volume. We're back to conservation of mass. We have to think about changes in density. However, then delta volume, and therefore delta rho, where rho is, you can still read that, density. But for starters, let's just think about we can think about conservation of volume in times when, for example, you have a soil column that's moving and it's not significantly changing in its density. All right, I think I've belabored that enough. So there are going to be several sections I go to below, but in this short clip, what I'm really going to focus on is just the conservation of mass itself. However, just to kind of give you an outline and a roadmap as to where we're taking all this, underlining conservation of mass again, to give you a quick roadmap as to where we're taking all this. So the first thing I'm going to discuss is the size of some imaginary box of mobile material, which I'm going to show in figure 3. Changes as a function of inputs and outputs. And so this is what we're going to do now. After that, we're going to, solve the equation that we're going to come up with for a situation that just has, with a hill that's entirely composed of mobile material. So think about like something like thick till, thick sand, and gravel. And that's really common up here where I'm teaching in Minnesota, where we have thick till and outwash deposits that blanket much of Minnesota and the upper Midwest. And so this is going to be number 1 thing that we're going to do now. This is going to be number 2 here. Number 3 is expanding this to incorporate aeolian deposition or erosion, which can act as a local source or sink of material. So you can imagine we talked about benefacting earlier and about removing material from aeolian processes. And we can also add materials to have things like sand deposition or loess deposition, which is silt. After that, we're going to talk about weathering and soil formation. So yes, what we learned about earlier in soils is going to come back here. And we're going to think about how depth to bedrock, if the hillslope is underlain by bedrock, which is the case in much of the world, might end up being important. And then we're going to think about how that affects the thickness of this mobile layer in bedrock-dominated landscapes. And then finally, number 5, we're going to talk about the fact that right now we're just saying that soil motion or mobile material motion is proportional to the gradient of the hillslope. But in truth, it's proportional to hillslope gradient and to the amount of material that's actually available to be moved, right? So we could parameterize a bedrock hillslope with just a really, really small case of M to say that there isn't going to be much material moving. But in the end, this sort of discharge should relate to some kind of velocity inside a layer in the hillslope. And so what does that velocity profile look like, and how can we add a few more elements of reality to this? And so this is going to be taking us a little bit of time to get through, But right now my goal is just to try to hit some of the main highlights, and in this short clip, to spend the rest of the time talking about conservation of mass. So going down here, this is our toy hillslope, and down here we have bedrock. We have some layer of mobile material here with H sub m, which is our mobile material thickness. And then up top over here, this is just air sitting above it. Z sub r is the elevation of the top of the unweathered bedrock, and Z is the surface elevation. And so that can be the elevation of, typically of the land surface. So in fact, this arrow should be going up a little bit higher. In fact, it is the elevation of the land surface. So I will have to fix this figure. There must have been something that happened to cause that particular problem. So this right here is Z. And if we look at, let's focus in on this little tiny box right there. And the reason that we're doing that is because then we have a zone where we can start to build up a set of all the processes that are affecting it and use this thing called calculus to be able to figure out how much material is moving in, how much is moving out, and what might be happening to make it thicker or thinner over time. So if we look at this box right here, I'm defining this box with the x limit being called x naught and the right limit being called x naught plus delta x. And so when we are dealing with how much material is being brought into it via weathering, we can think about how much material integrated over this whole distance from x naught to x naught plus delta x times weathering. So this is the weathering rate. Is being inserted into mobile material, and so this is the amount of material being removed from the rock and added to this mobile layer. We can also have deposition or erosion from the air, which has exactly the same form as this weathering relationship. There can also be dissolution of material. So in thinking about dissolution, so I just have this arrow going off into the middle of nowhere, but dissolution is going to act across the entire area. And so then we're also integrating from 0, which is down here, we're just defining this as 0, to h sub m, which is the thickness of the mobile material layer. And we're integrating across x naught to x naught plus delta x of d, which is the dissolution rate. And so that material is going to go out in solution, like, for example, out via pore waters that are moving through the hillslope. And by the way, since I was defining these other ones, this is going to be aeolian deposition or erosion. And the or is a little loose. It can be more of an and, or we can switch from erosion to deposition over time with shifting environments, climate, sediment supply. And so those are the other terms that we're thinking about. But right now, from more of our standpoint, starting out with the thinking about material moving laterally, downslope, we actually have this qm. So we have qm at x naught and q sub m at x naught plus delta x. And if we remember, we have this equation here, right? Q sub m is equal to minus khs times dz over dx. And so we can look at that difference between the inputs and the outputs to think about whether the hillslope, this section of hillslope, is going to be becoming thicker or becoming thinner over time. And so, in particular, let's think about this lateral conservation of volume in a hillslope element. So thinking about those inputs and outputs. So at some location x, and in fact, to make this consistent with our figure, I've got to update this to x naught. See, there are going to be a few updates to the notes. So I'm going to x naught plus delta x naught here. material is entering the box and leaving the box at these rates, which I'm going to give by little q and little q. So here's what we have now. I'm just going to draw this box, x naught plus delta x, and we have q sub m of x naught. Going in and going out, we have q sub m of x naught plus delta x. Well, how is the amount of material going in and going out going to change this h sub m, the thickness of material in the box? Well, we might think that if more material enters the box, so I'm going to draw an arrow coming in from the left-hand side that's quite a bit bigger, then leaves the box, then this box is going to get bigger. H sub m is going to go up. And likewise, if we have less going in and more leaving, then we might have h sub m getting smaller. Poor little h sub m. And specifically, if we're looking at this, we can think that of the fact that the changes in h sub m over changes in time, so this is t is equal to time here, by definition, is going to be equal to inputs minus outputs divided by the width of the box. Right, and so if it's a super narrow box, a little difference in inputs versus outputs is going to cause a very large change in the height, whereas if it's a very wide box, that same little difference in inputs versus outputs is going to cause just a itty bitty little change, because it has to be spread over that whole wide width. So hopefully that makes sense. And at this point, what I want to do is draw your attention to the right-hand side of this equation, equation 4. Does it remind you of anything? You have a difference divided by a width. And if I give you a second, as I slowly scroll down, maybe one of you is thinking back to early college, maybe high school, where you might have encountered something that looked a little bit like this, where and I've actually flipped this around. So now I have x plus delta x over here, minus x over here, and divided by delta x. If you think of delta x as h from calculus class, this is exactly the definition of a derivative. There you go. And so what that means is that, well, it would be the definition of a derivative rather if we took the limit as delta x approaches 0 of this whole thing. And so what that means is that this over here is going to equal dq sub m over dx. And that right there is important. And one other thing that's important is noting that I already flipped the sign right here, right now, right? So then this is actually going to eventually become a minus sign in front of that. So here we are. So if I'm trying to understand the difference in h sub m over dx, so we have dh sub m dt, but then this is dq sub m over dx. So I believe, let's just scribble this whole thing out. So one may then write this whole limit, and so that what we end up getting is an equation that's much more like this. So from this definition of a derivative, we have dqm dx. And I'm just going to, because I had the wrong equation written down here, rewrite this just to make it a little bit easier for you. So dq sub m over dx is equal to the limit as delta x approaches 0 of q sub m x plus delta x minus q sub m of x over delta x. So it's just the same thing I wrote above. I think that my brain was going to h's because of h's being used in calculus, so I apologize for that. We're just going to completely ignore that right now. So if we then take the limit as this delta t goes to 0 on the left side of the equation, we can actually put this whole thing back together, right? And so taking the limit as delta t goes to 0, so lim as delta t goes to 0 of delta h over delta t is equal to d h dt. Then we also have this limit as delta x goes to 0, and that's this dqm dx, and we know that we flip this around, which gives us a minus sign. And then what we have to do, because we have derivatives with respect to t and derivatives with respect to x, so we have derivatives in two different dimensions. In this case, space versus time. Mathematics doesn't care about space versus time, but gosh, I sure do. And so if we want to combine those two together, then what we need to do is switch these to the curvy d's. And so what we end up getting is dh over dt is equal to minus, to account for the fact that we flipped the sign around, dq sub m over dx. And that is exactly the equation that we have here. And this is showing us how we can conserve mass, and we can actually show that there's a distinct change. I'm going to add m's to all of these. A distinct change in the thickness of mobile material per unit time as a function of the gradient of material moving into and or out of the box. And so overall, what this is just saying is that the change in elevation of a thin imaginary box of material on the hillslope is equal to the amount of stuff that goes into it minus the amount of stuff coming out of it divided by the width. Therefore, the rate of change in elevation of this imaginary box is equal to the rate of material entering minus the rate of material leaving divided by its width. And so the only two difference between those two sentences was that the second sentence is talking about rate. And rate is where we start dealing with this dt right over here, so this time derivative. With that, and with my apologies for that slight confusion involving that miswritten equation, I've got a couple things on my to-do list to fix up. We have gotten to the point where we can talk about changes in Hillslope form as a function of changing material motion down the slope. And once we wrap up with this, the next step is then to combine all of those together and create a diffusion equation for how material overall moves down a hillslope.